All right, so in chapter 4, section 4, we're dealing with the logarithms. And so we're dealing with natural logarithms. So here we have an exponential function, e to some number equals a value. You could verify this on your calculator. Find the e button, raise it to the 0.35, you're going to get this. But you have to be able to go back and forth in between exponential functions and logarithmic functions. So to do this, it's the natural log of this equals this. So officially, when we're looking at in the book the definition of the natural logarithm, they're um, they're inverses of each other. Like if we were to graph a exponential function and then we do the log of that function, we are going to get inverse functions from each other. So once Desmos gets going here, I'll come back to it. So what you're going to do is, if you have something like this and we're rewriting it, so it's log base e, so there's our base, so that's a natural log, of this equals that. So these should be things that you've done in maybe like a pre-calc class. Another one to look at, something like number 6, the inverse properties of logarithmic and exponential functions to simplify expressions. So in the text, they have some of these rules for inverse properties of logarithms and exponentials. Also on this page is some of the other rules when your natural log of a product equals the sum of each individual natural logs. And we're going to be using some of these rules to solve. So, going back to Desmos, just like if you had e raised, let's do a 2 to the, or a 5 raised to the x, let's say equals y. This is going to be the inverse function of log base 5 of x equals y. And so, again, inverse functions, they are symmetric around this y equals x, and so we can clearly see that these are inverse functions of each other. For a natural log, what we're dealing with in section 4, we're dealing with e raised to the x equals something, and then the natural log of that, so it's log base e. Log base e is the same thing as a natural log, and we'll verify that in a second. So here we see the inverse function. Instead of writing log base e, it's just more common to write natural log of x equals y. And so we get that same line. When we get to problems like number 7, it's asking us to use some of those properties. So this is a division, so on that one page it says if you divide, you're actually subtracting. Natural log of x divided by y equals natural log of x minus natural log of y. So this would be the natural log of 1 minus the natural log of 13. But they didn't have a natural log of 1. If you explore a little bit, you'll find out that the natural log of 1 is 0, because anything raised to the 0 power is equal to 1. So natural log of 5 of 1, log base 5 of 1 equals 0. So whenever you have log base 5 of 1 or natural log of 1, you're always going to get that exponent, which is 0. Another way I like to think about it is if you're dealing with logs, this represents an exponents, right? This natural log represents an exponent value. So when we have something like e raised to something, when we're doing natural logs, we're solving for that exponent. See, we're solving for the 6. So there's a couple word problems that I want to look at, and I'll probably do a supplement for these. So like on number 11, solving for this. So we would all agree that we're probably just dividing both sides by 6, but when you have natural log of x equals 4, how do you get there? And again, that's going to be using the idea of going from a log to an exponential and how we go back and forth in between. So I'll do a supplement for that one. Also, like on number 13, a little bit more complex. But it's just an algebraic process, so nothing crazy as long as we know this rule of how to go back and forth between logs and exponentials. And then we'll maybe, this one maybe we'll do with Desmos to show how we can solve these using technology. So if I have this equation, like on number 16, so I get some p of x equals 1586 e raised to something with a t, 0.02, I'm going to call it x again. According to this model, when is the population? That's what our p is, the population. What was the population of the city in 2002? And so t is 0 corresponds to 1980. So if we're looking at 2002, well, that's pretty easy. We would just plug in 22, right? And we're going to get this 2462 point. But again, this is in thousands, so I'd have to move the decimal 3 places. Always be careful of your units. But also, according to this model, when would the population be 2.9 million? So basically, I'm going to be typing in 2900, right? So if I have a y equals 2,900, that's the same thing as 2.9 million, right? Or 2,900,000. So let's look at this. It doesn't like commas. So I get y equals 2,900. So let's graph this to view that intersection. And hopefully, since 1980 to 2010 is 30, we're going to get an x value of 30. So let's see if we can do that. Again, I'm dealing with x values or in years. So maybe I could go from year 0 to year 45. My y stands for my population. So let's go with 1586. It might be one of my low values. And let's go to 3,500. Because again, I know I'm looking for 2,900. Got an initial value of around 1,500. And where they intersect, I get 30.175. So let's go back to the question. According to this model, in what year? So if I'm 30 years after, 30.125 means I'm still in 2010. So 30.175, 1980 plus 30 is going to give me that 2010. And then that's just like, maybe we're in like February or something with that 0.175. So I'll do a supplement showing how to do, I believe it was like 13 and 11, how to do those by hand. But this should get you started on the 4.4 section.